Okay, we are recording. So welcome everybody to the third and final installment of our Let's Explore Quantum lecture series. Today we're going to be taking a broad and quick overview of quantum sensing and quantum networks. So we established in previous lectures that this new quantum revolution, the second quantum revolution that we are a part of, is held up primarily by three core pillars. Last week, we discussed quantum computing. This week, we're going to capture quantum sensing and quantum communications all in one. These each could deserve their own full-length lecture, but for the purposes of this program, I think it's sufficient to combine them. So we're going to start off. What is the quantum internet? Can anybody tell me what the regular old internet is? What is the classical internet?
Technology used to connect software to be able to connect to each other.
Good. Yeah, I like that. Anybody have anything to add to Abby's definition?
It's a protocol of exchanging packets.
Packets of what?
Data.
Precisely. Yeah, so both of you are right. The internet is a physical piece of hardware. It's a big old network of cables and computer, server banks whose purpose is to connect all of our devices and enable them to transfer information, whether that be videos, text messages, photos, anything you can store on your phone or transfer around is represented as a series of ones and zeros. Now, you all have been following along very well with these lectures. We've talked about classical information, classical bits, and also quantum information and quantum bits. And if the classical internet is something that you use to send classical bits around, could somebody guess what the quantum internet might be?
The internet to send quantum bits around like the typical internet sends its own internet with.
Yeah, absolutely. That's all. We're done. Lecture's over. No, but yeah, the quantum internet is a hypothetical piece of hardware, a hypothetical collection of cables and other infrastructure that we have to invent that will enable us to send quantum information from device to device. And what we're going to cover a little bit in this lecture is why would we do that? Why is that a good thing or an important thing or an interesting thing to do? Does anybody have thoughts just at this stage?
No, I do not.
Okay, I'm going to take that no, I do not, and keep going. So we mentioned that the internet is a physical thing, and I absolutely love this video, but we're going to take a few minutes to watch it, and we're going to understand that the vast majority of the internet lives and is comprised of data that is transferred in big, giant fiber optic cables that are stretched on the sea floor between continents. Very interesting piece of engineering there. Can folks hear the audio?
No.
Is anybody hearing the audio here?
No.
Nope.
Okay, let's try something. How about now?
No.
Well, sorry, 1 second. Got to get it playing.
Undersea cables. Why should you care? Because modern life is increasingly
about now?
dependent on those.
Can people
I can
hear it?
now.
Yeah.
Okay, let's start it over then.
99% of all internet traffic, from this video to your Pokemon Go account to your family WhatsApp group, runs on a hidden network of undersea cables. Why should you care? Because modern life is increasingly dependent on those slinky subaquatic wires. And they get attacked by sharks from time to time. How do they work? What's the future for them? Join us today as we plunge the depths and ask how the internet travels across oceans.
So I'm just going to stop it there. I'm just going to emphasize for a moment
99%
the fact that the internet is occasionally attacked by sharks. It's probably my favorite headline ever. And feel free to circle back when these slides are shared and watch the full video. It's very interesting. But the bottom line is the internet requires physical infrastructure, just the same way that you need roads for your cars to take you from place to place. The internet requires a medium through which information can travel. So when we think of building a quantum internet, the question becomes, well, what type of channel can carry these special types of quantum bits? And the first answer is actually pretty easy. The same thing we use to transfer classical bits, an optical fiber, can be used to transfer quantum bits. Obviously, you know, there's additional details there, but researchers who are building quantum networks, the foundation of the quantum internet, have occasionally been known to use existing optical fiber networks that were laid down long before the idea of a quantum internet was come up with. So quantum internet could be made out of optical fiber that, again, could be laid down on the bottom of the ocean or buried between important, you know, central buildings in cities. Another proposal that you'll see on the right is for the quantum internet to be mediated by special satellites, which transfer the information in the form of photons that are beamed up from your computer up to the satellite and are then relayed downward. And in fact, this is a photograph of a friend of mine. So her name is Kimia. She's a graduate student at the Institute for Quantum Computing, where I used to study, and her research focuses on a new quantum network satellite that Canada is going to launch in 2025, next year. So next year, Canada is going to be putting one of these quantum network satellites in orbit to test how it can be used to connect 2 points in Canada using a very basic quantum network. So these are real experiments that people are building today, and we are just now on the verge of seeing how these technologies work, and once the proof of principle is established, how we can scale them and network many more sites together with a more complex network of quantum relays. Questions here? Anybody have any questions on the hardware that we would need to build a quantum internet?
No questions.
Okay. So highly encourage you all to Google Canadian quantum network satellite, read some articles. It's very interesting. But to kind of motivate, you know, we've talked about the how, but we haven't really talked about the why. Why do people want to build a quantum internet? And there's a couple different applications. This isn't a complete list. Quantum networks isn't my full area, but these are the top 3 I hear discussed most commonly. So these are secure communication. We can use a quantum network to provide an additional layer of security when you send private messages, as well as some applications actually to enhance a quantum computing application. So these, you know, it's not an application that directly impacts us today, but distributed quantum computing, blind quantum computing may one day become important as we see quantum internet technologies and quantum computing technologies helping each other. But let's focus on the first one, secure communication, because that is by far the biggest motivation for building a quantum internet. Most people who invest in the quantum internet, who want to see quantum internet developed, they are thinking of QKD, that acronym for secure communication, which stands for quantum key distribution. So let's first talk about this secure communications idea. So let's say this is the kind of canonical setup. You have a person at location A, we'll call her Alice, sending a message to a person at location B, we'll call them Bob. And the premise of this is, let's say Alice and Bob are discussing a preliminary idea for a startup, and they want to keep the idea for the startup secret so that they can have as much of an early mover's advantage to grow their business and really take the market by storm. The challenge might be that you could have Eve, an eavesdropper, who might intercept their communications, learn about their startup idea, and steal their idea. So this is a context where we would want to motivate, you want to make sure that your communication is as secure as possible. And to do that, you can utilize quantum key distribution, or that's the idea. If you had this infrastructure in place that allowed you to send quantum information, for example, let's say you had one of these nifty satellites the Canadians are launching. Well, then if you had access to one of these satellites, Alice could send information to Bob in the form of qubits. They could send information back and forth to each other. And using this quantum information, if Alice sends Bob enough qubits, Bob will be able to reconstruct their message, the information about this startup idea, in such a way that the eavesdropper cannot access it. And the way that that works, we've talked in previous lectures about how delicate quantum information is, how fragile it is, how you have to really carefully engineer the circumstances so that your precious qubits are protected in their journey from Alice to Bob. The idea of quantum key distribution, in quantum computing, this fragility is a big problem. And we talked about that last time, where if you want to build a big quantum computer with a bunch of stable qubits, their delicate nature is actually one of the defining engineering challenges. But in quantum key distribution, we take advantage of that fragility to produce a signal that someone is listening in. So the idea goes like this. Alice is sending qubits to Bob, but if Eve starts listening in, Eve will disturb those fragile qubits in such a way that Bob will instantly be able to tell that someone is intercepting their messages. And once they know that they're being listened to, they can switch to a different channel that's more secure, and therefore they can protect their idea, their communication from being eavesdropped. Questions about this? That's the idea of quantum key distribution. It's a way to exploit the fundamental delicate nature of quantum states, like qubits, for the purpose of creating a signature that someone is intercepting your messages, therefore giving you the ability to secure your communication, because you can always switch to a new channel that isn't being listened to. Questions about that?
No.
All right. So we're going to move on from quantum key distribution. The bottom line is this first reason people want to build a quantum internet, quantum network, is it enables these channels for secure communication. Let's move on to a second reason for building a quantum network, which is to network together small quantum computers into one much larger quantum computer. We talked about this quantum internet being a way to send a bit from one computer to another. Well, now imagine that you are networking together quantum computers. And when we spoke last time about quantum computers, one of the big ideas was that quantum computers right now aren't big enough. They don't have enough qubits to accomplish any computational tasks that are important. But if you could network these computers together, let's say Jackie has a couple qubits in her lab, Pavel has a couple more in his lab, we all network our computers together using a quantum internet, then we would in effect build a much larger quantum computer that is shared among our resources. So this is the idea. The idea here is that quantum networks may one day assist the project of building large enough quantum computers to be useful. But again, this is what I call a secondary application. It's not an application to a technology or to the world as it exists today. It's an application to a hypothetical technology like quantum computing that may exist later on. So think of it as you know, I think of this as much more speculative than, say, quantum key distribution is. Quantum key distribution, people have already built small networks of those that work. But distributed quantum computing, or the other application which you may have seen on the summary page, blind quantum computing, those I see as taking place much farther in the future, and therefore are less certain that they will come to be. But we're now going to move forward to discuss sensing. Does anybody have questions about networks in general before we move forward? This is a bit of a shorter lecture, as I mentioned.
No question.
Okay. So moving on, what is quantum sensing? And this should actually have a little bit of a special importance to us because we are all here working together in the context of QSense. QSense is a Quantum Leap Challenge Institute funded by the National Science Foundation specifically to advance the technology of quantum sensing. And quantum sensing has a lot of different types of application, a lot of different technologies that are used for those, and a full lecture on quantum sensing is a little bit beyond the scope of what we can do here because the details of the setups become a bit technical. But the overall idea is that if you have heard of us discovering gravitational waves, and you haven't heard of it, Google it. It's amazing. But we can essentially detect fluctuations in the fabric of space-time in part because of quantum sensing technologies. In more, examples that are a little closer to home, the sponsor, one of the sponsors of our hackathon, Inflection, is building a quantum sensing device for the application of navigation in the top left. And many researchers at CU Boulder are specializing in a type of quantum sensor that might one day be useful for detecting underground, subsurface detection. So, there's different ideas for why you might want to do that. The most leading one, probably the one with the most money in it, is detecting underground reserves of oil or natural gas. And we'll get into discussing some of the societal impacts with an ethical dilemma at the end here. But from medical scanning to new ways of imaging objects, quantum sensors have a really wide range of applications. And I'll say this, with quantum computing, with quantum networks, with all of these technologies, I have been clear that none of them yet are delivering value. They don't work yet. We are hoping they will work someday. And how long it will take quantum computers to start working or quantum networks to become useful is unclear. And in some sense, it's unclear how long it'll take for quantum sensors to become useful. But if I were to guess, if I were to tell you which of those three pillars, sensing, networks, or computation, are the closest to delivering value, it would be quantum sensing. So quantum sensing really should take on a special role in those three pillars and should be thought of as being particularly close to being useful in the near term. Obviously, I don't know the future, but that would be my prediction. So let's talk about quantum sensors. Quantum sensors can be used, as I said, for a wide array of applications, from sensing fine differentials in the field of gravity on Earth to navigation, as you can think of. We'll talk a little bit more about how exactly they do that, to enhancing existing technologies. We discussed in the very first lecture about how MRI scanners actually utilize quantum phenomena to image your tissue. Well, people have found ways to enhance the accuracy and the precision of MRI scanners using new quantum techniques. And we can also use them to detect fine differences in electromagnetic fields, which is highly useful for material science. So let's dig into a little bit more detail on these applications. Let's talk first about the inertial sensors. And I wanted to start with this because our hackathon sponsor, Inflection, specializes in this technology. And the basic quantum nugget you need to make this work is a simple atom that we can see on the right. And in fact, you need a whole bunch of them. And this is what Inflection does. They'll collect a bunch of atoms. And Abby actually submitted her hackathon submission for this Inflection. Abby, could you tell me a little bit about what comes next if you want to make a Bose-Einstein condensate for Inflection?
So the challenge I did for them was splitting, I believe it was electric field line in almost exactly half.
So you're splitting one of these clouds of atoms.
Yeah, clouds of atoms. I almost got it almost exactly in half by creating a barrier using Python. Yeah.
Nice.
So
and in these experiments, it's not just individual atoms. what's special about this type of quantum sensor is that you are taking these atoms and you are turning them into a new type of matter. So we've got, actually, Pavel, could you tell me what are the common phases of matter that we might learn about in an intro chemistry course? What are the types of matter that we find in the universe?
Gas, liquid, it's hard state, and plasma.
Yeah, so I heard solid, liquid, gas, and plasma.
Yeah.
Bravo, very good. That's exactly right. But what we're finding with quantum is that we can create new phases of matter. So a Bose-Einstein condensate, it's just called that because a guy named Bose and Einstein together predicted this thing. And then in 1995, they made the first one actually here in Colorado. So a Bose-Einstein condensate is what happens when you take a bunch of atoms, like Abby did, and you cool them down to colder than the vacuum of space. Again, we've talked about before how important that is to get quantum effects to manifest. We need our experiment to be very, very cold. And when that happens, the atoms begin to blend into each other. So think of you're creating almost a super atom where all of the atoms in your experiment have merged into the figure that you see in the front, which is called a Bose-Einstein condensate. Very cool stuff. And you can make these at Inflection. So what Inflection does, the first step of their process that Abby worked on, is taking this condensate that's in the moment just a lump and splitting it into two parts that then interfere with each other. This is a quantum phenomenon we haven't talked too much about, this interference. But it's this idea that the atoms aren't behaving like particles. They're behaving like waves. And in just the same way that if you have a bunch of little sound waves, they can all add together into one big sound wave, that's your Bose-Einstein condensate, then you could split that Bose-Einstein condensate and get it to interfere with itself. So this is, kind of like creating a noise-canceling headphone. And the idea, what they found is that if you have this interference pattern actively being monitored on an airplane, then as the airplane flies in different patterns, you will get a different interference pattern in the Bose-Einstein condensate. And so you could have a plane whose GPS device breaks. And by monitoring this Bose-Einstein condensate, you can still know how you have changed your trajectory. And since you know your starting point, you'll be able to tell where you have ended up. So you can use these Bose-Einstein condensates for navigation, which is mind-blowing. Do people have questions about this? We're going to move to another application. Okay, moving forward. The next we're going to talk about is magnetic and electric sensing. So these are actually technically two separate technologies, but I want to motivate a little bit why we should care. We have compasses. Those are magnetic sensors. We have devices that can detect electric fields. So why would we want to build a quantum magnetometer? There we go, got it out. Why would we want to build a quantum device that could measure tiny fluctuations in a magnetic field? Well, let's imagine that you are a material scientist and you're producing different types of materials, and you can imagine that the materials that you're making have little sections, which you can see visualized on the figure on the left. And these little sections have a magnetic field of their own. And you can see on the left, they're all pointing in different directions. So you could use your quantum magnetometer and you could sense, oh, all these magnetic fields, they're all pointing in random directions. So then you can go back and you can make a new material with the magnetic fields of all the different regions aligned with each other. And does anybody know what that type of technology is when you can build, say, a metal where all the magnetic fields of its smaller components are aligned. Do we know what that's called? It's a magnet. So this is an example of how you would use this to engineer a basic technology that we know how to make already. But if you have a material where all the magnetic fields are aligned, that's a magnet. And this actually, this diagram comes from showing how you make a magnet. You melt it so that these components with the magnetic fields that are pointing in different directions become fluid. And then you subject them all to a magnetic field so they all align, and then it cools, and now you have a magnet. Now, hopefully that kind of gives you a sense that if we have this very fine-grained, incredibly precise ability to measure tiny fluctuations in magnetic fields. And by the way that they do this with quantum sensors is they take diamond and they engineer them to be able to detect these magnetic fluctuations. We're hoping that these types of magnetic or electric sensors give us a new way to see the materials that we're making. And hopefully that new way to see will help us find our way to making materials which have properties that we would really like. For example, the holy grail of material science is a room temperature superconductor. And that's often cited as one of the pie in the sky goals of these quantum magnetometers and electric sensors, is to use them to help us discover ways to make wires that have less electric resistance, and therefore they waste less power. Question on this. We're going to move to another application. We're doing these kind of rapid fire, and it's okay if they don't all make sense at once. I'm glossing over a lot of the technical details. So if there's gaps, it's because I couldn't talk about it without using math. Questions here? Okay. I'm just going to keep on going. So one of the last ones that we'll discuss in detail is building a gravity sensor. So this one requires a little bit of background knowledge. But what I'll tell you, the cliff notes, is that back in the day when Einstein came up with general relativity told us about an experiment we could run. And the experiment goes, if you put a clock at the base of a tall, tall building, and you put a clock at the very tippy top of that tall building, those two clocks will tick at different speeds. And Einstein's general relativity shows that's because the clocks are actually experiencing time differently, which is a whole thing we don't have time to get into. It's a very deep and beautiful and interesting. But the bottom line is, as you move farther away from the surface of the Earth, your clock will begin to tick faster. So let's imagine we had a very, very precise clock. A clock that is so good at measuring time, it can detect if I've lifted it just an inch above the table. That technology has not existed for a very long time, but today it does. And the image you see on the right, we're going back to atoms. Atoms appear to be very useful as a basis for technology. By monitoring certain properties of the resonant frequencies of atoms, people can use them to build clocks that are so sensitive that they can detect centimeter, inch, centimeter differences in height above a table. And so what you have effectively built with these atomic clocks is a device that can detect how strong a gravitational field is. If they can tell how far they are away from the Earth, they should be able to tell if they're being held above a very dense portion of the Earth or a less dense portion of the Earth. And this is how we're going to come around to that application I mentioned in oil drilling. Because oil companies would love to know if there's a pocket of natural gas somewhere, and the natural gas will be less dense than the surrounding rock. Now, today, atomic clocks are not yet precise enough to enable oil companies to do this. But this is just an example of a technology that may have a debatable or a questionable ethical application. It's not just that, gravity sensors aren't only useful for this, but this is one of the largest investments, one of the largest interests in this technology, is for oil companies would like to have the ability to just sense pockets of natural gas or oil underneath the ground to tell them where to drill. And that leads us to the ethical dilemma that will conclude this lecture. I'll end the recording in a moment to give us all a chance to think about it and discuss. And for folks watching the video online, feel free to consider this as you walk away from the video. But we've just discussed a large swath of applications of quantum sensors, and they fall maybe on a spectrum from amazing to questionable, from using them for quantum MRI that could give us a much more precise understanding and view inside of the human body for better medical diagnostics and ultimately better health outcomes, to using not the same sensing technologies, they're different. The gravity sensor and the quantum MRI rely on different tech, but a group that gets funded to do one may be able to develop the other. And do we need sensors that empower the oil industry to continue to contribute to the climate crisis? That's a values-based question. It's not for me to say one way or the other as an instructor what the right answer is. That's why it's an ethical dilemma. But I'm going to pause it here so that we can have a chance to think about this and perhaps discuss without thinking that our ideas or our views might be recorded. So I'm going to pause there.